Good morning. Welcome to the Core Principles track. And this is going to be a Core Principles talk about implementing distributed consensus. A short disclaimer, I was asked by legal to point out that this work is not affiliated with any company, including Google. This is the result of a personal education project that I finished before I joined Google. So what is this about? I heard a lot about distributed consensus, mostly from conference talks, but I never heard about it at university. So there was a gap of knowledge. My formal education, distributed consensus, and distributed systems in general were not really part of it. But I wanted to understand it because it's important for my job. And since I'm not very good at reading papers and then getting a picture of what it is, I had to implement it myself. And that took a bit longer than expected. I like to share my journey today, the mistakes I made, the challenges I faced, and also a bit about how distributed consensus works. So this talk will be going from a theoretical overview, slowly moving into actual code, and we can see all the stupid mistakes I made. But first, a bit about distributed consensus in general. There are a couple of protocols out there, Paxos, Raft, Zookeper, Atomic Broadcast. You could argue that proof-of-work systems like Bitcoin are also producing a distributed consensus, although it may be a bit too slow for what we usually face in production. And my favorite game, Age of Empires, also had some kind of distributed consensus protocol. It's called the lockstep anti-cheating protocol. I never looked into this, but this is something I really have to do. You probably have seen a couple of the implementations already. etcd, for example, that is part of Kubernetes, is a distributed key value store, or Apache Zookeper. And some people maybe have heard of Chubby, which is a coarse-grained log service that is internal to Google, but described in a public paper. Today, I'd like to go into Paxos. That is the only distributed consensus protocol I really looked deep into. A bit of the theory. Super boring. In Paxos, we have different roles. The client role, the proposer role, the acceptor role, the learner role, and the leader role. And I'd like to start with the client role to describe what happens. The client, seen in yellow on the slides, could be a system that needs a consensus on a value X. So this could be maybe a front end that wants to write to a file and needs to have a lock on the file. Locking is the classical example for distributed consensus. So the client asks a proposer for a consensus on value X. Then the proposer has the proposer role needs to act on behalf of the client. It advocates the client request, and it asks other roles, the acceptors, if they could agree on the proposed value. And by doing so, the proposer is the one who moves the protocol forward. The acceptors are also sometimes called voters, and they are the fault-tolerant memory of the overall system. And the group of acceptors forms something that we call a quorum. And the acceptors, we'll look later into how they decide, could decide to, yes, sure, X sounds fine, let's all agree on value X. And if they do so, they inform the proposer, but they also inform the learner. And the learner's role is to add replication to the protocol. They take action on learned or agreed on values. So one action could be, for example, responding to the client. Because eventually, the client wants to know, have we successfully agreed on value X? There's a special role called distinguished proposer, or I would call it the leader here. And that is when we have a proposer and we decide that via software that this is the only proposer that is allowed to make progress. And this, if the protocol allows for something like this, and this means this kind of solves the problem of leader election already. So this is why Paxos is also often used to elect a leader in a system. So this would look like this. We have two clients. Each client wants the system to agree on a value, but only the distinguished proposer, the leader, is allowed to make progress. So client 2 will make the system agree on a value. Client 1 will not be successful. Now, this is all a bit too much. At least it was for me. And then I found out what we actually do in practice when we implement such a system. We coalesce all the roles into one piece of software. So forget everything about the different roles, and everything that all these roles do, we just do it in the same piece of software. So now we call the entity a processor, P+ in the slides. And a processor has the roles of proposer, acceptor, and learner. And clients can talk to any processor to make progress, but it would make sense to maybe talk to the nearest one. Whatever near means, it could be in the same data center, or it could be maybe miles or continents away, but with a faster connection. So over the network, it looks nearer. We could also elect a leader and make all clients talk to the leader so that we can make faster progress. We will see later why leaders make faster progress than other proposers. So how does it look at scale? Basically, a system of processors, of P pluses, is a complete digraph. That is a directed graph where every pair of distinct vertices is connected to a pair of, by a pair of unique edges. So it looks like this. Basically, everyone talks to everyone. So if we have n proposers, which we would also call the quorum size, because every proposer is an acceptor, now the whole thing is called the quorum. We would have n times n minus 1 connections. If we have a leader and we decide that only the leader can make progress, then only the leader needs to talk to everyone else. So that means we can have a significant reduced number of connections between these processors. So with the same quorum size, we have much less connections, and this would be n minus 1 connections for a quorum of n. How does it look at scale? This could be a bit hard to read in the back, so let me show you. We have this line that goes up, that is without a leader, and on the x-axis we have the quorum size ranging from 0 to 25. On the y-axis we have the number of connections that we need, and without a leader and 25 processors in the quorum, we are way above 600 connections. If we have a leader, it scales linearly. Again, this is all theory, because when I looked a bit deeper into it and started implementing it, I found out we never really have any quorum larger than 5. It doesn't make sense. So I talked to a couple of experts on this, on distributed consensus, and they all agreed the maximum we ever see in a system, like in most systems at least, is 5. So a leader makes a protocol a bit faster, but from a point of scale, it is not really needed. So we can start implementing it, the whole protocol, without a leader first, which should be easier. There's some limitations to Paxos. So originally, only a single consensus can be reached. So that means once we went through the protocol, we always have to stay at the agreed on value. That doesn't make much sense, because sometimes values change in a system, and if we would know that the value will never change, then we could make it a constant in the code and would not need to have to implement all this stuff around it. So what we do is, when we finish the Paxos run, the system opens up to do another Paxos run to agree on a new value. This could include overwriting the old value, but that is part of the application logic. Another interesting limitation is multiple proposers may believe to be the leader. So if we have a system with a distinguished leader, but two processors in the system think they are the leader, then they duel each other. to win the value. I ran into this, we will see this later. And standard Paxos is not resilient against Byzantine failures. That is, if a proposer has bad code or if a processor is made out of some, well, there may be some coding errors in there, or it's just maybe just bad or it got hacked, and tries to cause some trouble in the protocol is not resilient against that. There is a Byzantine Paxos protocol that is resilient against that. I did not look into that. Okay, so much for the theory. To really understand it, I had to implement it. And I thought, how hard could this be? It took me over half a year. And I'd like to introduce a software that I call Skinny. It is Paxos based. It's minimalistic. It is educational, so it errs on the side of having more log files than less, for example. It errs on the side having more readable code than performant code. And it provides a single log. So it is the smallest implementation of a distributed log service, I would say. Some features. It is designed to be easy to understand, at least as easy as I think it is possible to make. But if it's possible to make this even easier to understand or even more valuable from an educational point of view, I'm happy to rewrite parts of it. It should be relatively easy to observe. So there's the possibility to dump the state of the processors, for example, to see inside the system. It has coalesced roles, so everything is in the same piece of software. I found this easier to understand than writing a single piece of software for every role. And it provides a single log. And the log, like in all the log services that I know, the log is not observed. It's not enforced. So logs are always advisory. The clients have to make sure that they don't break the system. It's written in Go. It uses protocol buffers for serialization and gRPC for the connections. And please don't ever use it for anything that is related to production. So what we will do, while I go through how the software works, we will assume that we have a wide quorum. A wide quorum meaning I distributed 5 instances of this Skinny software all around the globe. That is not good practice. Let me repeat. We don't do this in practice unless we really need to, because it gives us terrible latency. We have a global consensus, that is awesome, but most often we don't really need it. So this gives us terrible latency. We can really see the system working, and this is why it's so perfect for education, because we can see the system working. Please note that this is something we only do to learn more. So let me quickly go through how Skinny reaches consensus. So this will be Paxos all over again, but specific to how Skinny works. We have these 5 instances. This is a Skinny quorum. I took the number 5 because the examples work best with 5, and also this is what the expert says, what we see in real life. So we have Beaver. Beaver is a client here. Beaver asks one of the instances, could I have a log, please? And now we're dumping state. So these gray rectangles, this is a state of the instances. The instance number 1, that is the bottom right one, has changed the internal state because Beaver asked for the log. We have something that we call the ID or the run number. That is the number of the Paxos run. As I said, we are able to make multiple runs to make the software useful. There's a value called promised. We'll see in a minute what it does. It basically holds a number of a future run. And then we have holder. The holder is the value that we agree on. So what Beaver eventually wants to see is that all the instances agree that the holder of the log is Beaver. So we want to put the string Beaver in there, but only if everyone agrees, or at least if a majority agrees. So the instance number 1 wants to start a new run, and it decided the ID of the next run, which must always be higher than the ID of the previous run, should be 1. So this is why I changed the promised value to 1. It promises itself that if there's a Paxos run with the ID number 1, it will believe the value that is proposed. And then it sends out a proposal to all the other instances. Like, I would like to propose a Paxos run with the ID number 1. How do you guys feel about it? Everyone checks their internal state. A new run with the ID 1 would be higher than the last run that I've seen. They have not seen any run, so the ID is 0. That sounds good to them. It's a simple comparison. If the promised value is higher than the ID, they will be fine with it. So they all change their internal state, promised equals 1, and send back a message. Sure, I promise you the value 1. If you start a Paxos run with the ID number 1, whatever you propose as a value, I will accept it. Now comes the commit phase. So the instance number 1 now knows that all the others are fine with that run. It sets the internal value for ID to 1, because that is a run that is now going to start. And it sets the value for holder to beaver. So the first instance already has the value. Let's see what happens. A commit message is being sent out. And it contains the ID again. So telling everyone, please, you promised me that the run number 1 will be fine with you. Here is run number 1, and the value that I want you all to commit to is beaver. And this looks all good to everyone, because they promised number 1, and now number 1 comes in, they will accept the value. We have basically reached consensus here. We have a majority, 5 of 5 is the greatest majority that we can get. And everyone agrees on that beaver should have the log. Out of courtesy, they sent out a commit message. As far as I understood, this is not really needed to make the protocol work. But I like if software is friendly and easier to debug. So we sent out the commit message. And then finally, a message goes back to the client, to the beaver. You got the log. Great. What happens if an instance fails? More or less the same scenario. Beaver still has a log. We had a couple of more Paxos runs, so we are currently at run number 9. And now a data center is on fire, and another one, and 2 instances are lost. Happens all the time, right? An SRE comes, fixes the data center, the instances come back up, but they lost all their state. And now Alien comes, and Alien would like to have the log. And for some random reason, Alien likes to talk to one of the instances that just came back up, that lost all their state. Let's see how the system behaves. The instance number 3 thinks of a number for a next Paxos run. And it comes up with a number 3. That is no coincidence. Because we would like to avoid everyone coming up with the same number, we have something that we call an increment in each instance. So that means every instance has a different number that it adds to the last run if it promises a new one. And to keep things simple, instance number 3 always adds 3. So to instance number 3, it promises itself number 3, it looks fine, and sends out the proposal for number 3. And now the other instance who just came back up, that looks fine. That looks fine to this instance. It had ID number 0, the promised value is higher, so sure, this could work. So here we have the first promise. But then something happens. The other instances, knowing that they were already at run number 9, and the run number 3 is lower than 9, cannot reach consensus, they inform the instance, I don't promise you this value, and by the way, I know of a previous Paxos run, which means a previous consensus that this Quorum had, with the ID number 9, and the holder was beaver. Okay, now the instance number 3 has a lot of conflicting information. It got the promise, it got not promised, it knows about the previous consensus that has been reached. What it does, it takes the highest previous consensus number that it can have, and that was 9, and it takes the value of that. So whenever someone informs an instance about the previous consensus, we should better believe this is what the majority thinks. And the highest number wins. So this instance, in the instance number 3, now thinks we are at Paxos run number 9, which is correct. It now thinks the holder should be Beaver, which is also correct. And it sends out a new proposal with the ID 12. So 9, adding 3, sends out a new proposal. I'd like to have a new Paxos run because the previous one failed. ID number 12, or promise 12 sounds good to everyone, so all the instances agree. We will promise you the next commit. And then the instance commits the learned value, not the alien that initially was requested, but the learned value, which is Beaver. And that brings everyone in the same state again. Now the full Quorum thinks we are at run number 12 and the holder of the lock should be Beaver, which is true. And then alien gets a bad message. Sorry, the lock could not have been acquired. The holder is currently Beaver. So if the application really wants that lock, it has to wait, or on the application level, maybe talk to Beaver and ask to release a lock, or maybe alert someone to do something. But usually if a lock is not acquired, there's a good reason for it. Okay, let's now, after all the theory, go a bit into code and see how this works. Skinny has a couple of APIs. As I said, I'm using protocol buffers. So we will look at the APIs in a minute and see how they look in code. The first API is the lock API. It is used by clients to acquire or release a lock. So that is a protocol that is spoken between the client and whatever instance it talks to. We have the consensus API. This is what is being spoken between the instances to reach consensus. So think of propose and commit, for example. And we have the control API that is purely artificial, and that is only used by us to dump the state of the system. That is not really required for a system to work, but since this is an educational log service, it is nice to see the state of each instance and find out where something is not working as expected, or where a code change, for example, led to an interesting output. That was really necessary for me to write the code because I had a lot of invalid state in my code. The log API. 2 messages, acquire request, which simply is the client sending a string, hey, I'm Beaver, so we trust the client that it knows its name. There's a lot of trust in the protocol. And a response message, whether or not it has been acquired and who the holder is, because it could be that the message is you have not acquired it, someone else is the holder. A release request is basically empty, just saying release a lock, and then we get a response whether or not we were able to release a lock. The service is also just consisting of acquire and release RPCs. The consensus API is a bit more complex. We have a promise request where we send the ID of the next Paxos run, and we have a promise response that tells us whether or not the value has been promised, the ID of any previous consensus, and the value of any previous consensus. And the commit request is similar. We send the ID of the run, and this time the value that we want the Quorum to agree on, and then the commit response tells us whether or not the value has been committed. Again, I think the commit response is not really needed. This both is exposed as an RPC for promise and commit. And the control API has a super simple request. It just sends an empty message, please dump your state, and we get back the full state. I'm not going to go into detail. it's basically all the variables that are worth exposing with a simple RPC. What did I learn along the way? So let's talk about the interesting part and all the learning opportunities. First thing, reaching out. So I had my instance, more or less empty. It was a server that got the auto-generated gRPC methods, and now I wanted to reach out to the other instances, because eventually all the instances need to talk to each other. Every instance has a list of peers containing all the other instances in the Quorum, and every peer has a gRPC client connection and a consensus client. So you don't have to remember this. The thing is, if we have a peer, we can just issue an RPC. That's kind of the things we get for free with gRPC. Now, the propose function. The purpose of the propose function is to send a proposal message to every other instance in the Quorum. So we have a list of peers. We range over it, and then every peer has a client, and the client has a promise RPC. And in that promise RPC, we send a message, the promise request message, and then sooner or later an answer comes back. And if it's not an error, we look into the message and see if it has been a promise, then we count it as yes, and if not, we don't count it as yes. And then there's a learn function, because it could be that there was previous consensus on something. We'll ignore this for now and just shove it into a learn function, and let's assume it will take care of it. So that is the most simple way of reaching out, but it has some flaws. So what happened then was I sent out a proposal, I count the value, I learn maybe if there's something to learn, and then I sent out the next proposal, and the next, and the next. This could be faster, but it could also be slower. So what happened is, luckily, I got a network issue. Otherwise, I might not have noticed this. And this happened. The proposal number 3 took a really long time because one of the instances was down, or I think it was responding slowly. So there's some risk in this and how I designed the system, that we can wait for a long time. If all the network is slow and all the proposals are slow, we will wait for a very long time for a response. So the first thing I did to improve it was limiting the waiting for I/O. So how I want the system to behave is like this. We have this proposal number 3, and it's taking a bit too long. So at some point we cancel it, we count it as a no, and we continue with the next proposal. This looks like this in Go. Go has this awesome concept of context, which I really like. And what we can do there is, when we issue a request, we can just put in a context with a timeout. So that means after, in this case, 3 seconds, in the example, it's just hard-coded to 3 seconds. After 3 seconds, we will stop waiting for responses and cancel the whole request and continue. In every case, we need to call cancel, even if you got a response. That is to prevent a context leak. So now it looks like, and now we have these requests, and no request takes longer than 3 seconds. The next improvement is, how about concurrent requests? Why not reach out to everyone at the same time, and then count the responses as they come in? So what I wanted to design here is something like this. We have the proposal, we send out all the proposals, and then when the last proposal is in, we count the responses, whether or not we reach the majority, and we synchronize on the learning if there's anything to learn. So concurrency is easy in Go. We can just kick off a Go routine. So we have the Go routine here. We still range over the list of peers, but for every peer we kick off a Go routine and proceed to the next peer. And in that Go routine, we have once again the context with a timeout of 3 seconds. So that means instead of 4 times 3 second maximum time, we will now have something slightly above 3 seconds for all of the requests. And when the Go routine exits, we call the cancel function to prevent a context lead. So if you look at the code, we can see that I issue the request, the promise request, and then there's a comment, now what? I was stuck there because now I need to count all the yeses that come in or the nos that come in, but I can't count them in the Go routine because the Go routine only sees this one request. And once the Go routine dies or exits, the value is lost. What I needed to do is introduce some synchronizing. So what we want to do, we want to send out all the requests. When we get the responses, we want to process the responses sequentially. And it's not important which one came first, but we have to see all of the responses to make a statement of whether or not we have reached a majority. So I did what every good programmer does. I came up with my own struct because we need more structs. And it basically contains whatever is also in the message, and also a string telling me where the message came from. This is to have better logging. Otherwise, I would not have needed this struct. And then we can use in Go this awesome synchronizing technique, which is a channel. So I make up a channel, and in that channel we'll put in the responses. And in the Go routine, we just create this response object, copy the values that were from the original gRPC response, and send it to the channel. And then the Go routine returns. But in the channel, we have preserved the response. And now for the synchronizing, the first thing we do now, we count the yeses and the nos. And the yeses start with 1. They start with 1 because an instance sending out all these requests made a proposal, and we would never make a proposal that we don't believe in ourselves. So yes gets a bonus and starts with 1, while no starts with 0. We always vote for ourselves. We range over the channel of responses, and whenever the response was positive, we count it as yes, and if not, we count it as no. And once again, learning something, let's ignore this for now. So looking at this code, something is wrong. What happened, I started all the instances. I started to acquire the log, so all the messages were sent out, and then nothing. Then the system was just stuck, and nothing ever happened. So there are two things here. We did not close the channel. So that means the range is blocking forever. I need even more synchronization, because once I'm done with all the responses, I need to close the channel so that when I range over the values in the channel, it will at some point unblock and continue. So yay, more synchronization. I'm using a wait group, which I think is the right tool for the job here. And the wait group is basically a counter where you can add a number and you can subtract a number. And when the wait group reaches 0, there's a function called waitGroup.wait. The function will return. And if the value is not 0, it will not return. So we can leverage this. We start with a wait group before we go into the looping over the peers. And for every go routine we kick off, we add a value of 1. So that means the wait group now has the value of the wait group is the number of go routines that are currently in progress. And in the go routine, as soon as it finishes, defer here means execute when the function finishes, we subtract one number. That means the moment all the functions have returned, the value of the wait group should be 0. And then we kick off another go routine, because we like go routines, and this go routine just blocks until the wait group reaches 0, and then it closes the response channel, which means that the execution of the code, which is probably at this point already at the last line in this code example, has a chance to at some point unblock and continue. This is how it looked like. I sent out all the proposals, and as soon as the first response came in, I started learning and counting. So, some more challenges, because now the code was working and it was stable and reliable and things happened, but then on a higher level, I ran into problems. I think at some point, one of the instances was down for some reason again, and I realized I can still reach a consensus, but it takes me 3 seconds, because I was waiting for the last response and the timeout was 3 seconds. Why not stop earlier? Why not stop as soon as I have a majority? And this is how this looks like in the Quorum. We won't go to the code for this one. I sent out the same proposal, the first proposal, then the second proposal, and so on, like in the code example before. So now all proposals have been sent out. And here the first promise comes in. So that means we have now 2 yeses. The first one is because we always believe ourselves. The second one is came just in, and now the third one came in. And 3 in a quorum of 5 is a majority. And now I can stop caring about all the other instances. Are they online? Are they working? Are they responding? I don't care. I cancel all the requests and move on. Yeah. How does it look like in code? First, we use one context for all the outgoing promises. So that means if we cancel the context, all of the requests will be cancelled. In the Go routine, not much new here. We still call the RPC and we still put the response in the channel, but the error handling changes a bit. And that is, the error now could be a general error, like something went wrong, I don't know, the network is down, whatever. And those types of errors we would like to count as a no. But it could also be that the context has been cancelled because in some other path of the program we decided we got a majority and we are not interested in the answer anymore. So if we have the type of error that indicates a cancelled context, we want to return without putting new values into the channel, because a decision has already been made. There's no value in putting more stuff into the channel. If it's any other type of error, we want to put something in the channel because we want to count it as a no. The function that closes the channel looks the same, nothing changed here. And in the counting and learning part, there's a small change. So we still count. If promised, then yes. If not, then no. We still learn. There could have been previous consensus. And as long as the request is not cancelled, we will check with every time we pass a response if the majority is either for yes or for no. We could have a majority for no, so we have to check this as well. And if that is the case, we cancel the whole context, set the value cancelled to true, or the variable cancelled to true to just avoid going into this part of the function again, of the loop again. is probably not really performance relevant. So is this fine? It is not. It is almost fine. Depends on the configuration. So I got this working and thought, oh cool, now I figured it out. And then I lowered the timeout values to see how the system behaves if I try to tune it a bit. And then something happened that I would call the ghost quorum effect. There's probably a professional term for this, but this is what I think it should be called. And the following thing happened. The timeout was too tight because, please remember, we are working on this global, on this wide quorum all over the world. And I was running these experiments out of my home in Munich, and Sydney is a bit away, even network-wise, from Munich. So some of the instances always timed out. It were always the same two instances that I was ignoring the answers of. And this is a hidden reliability risk. Because, let's assume this happens. One of the three instances dies that we are working with, that always respond. And the other two just run the timeout all the time. So that means they are not really there. They are there, but we're ignoring them. So now from a quorum of 5, because of a configuration issue with a too tight timeout, we managed to reduce it to a quorum of 2. And that will not ever get a majority. Another interesting thing I ran into, I mean, it had to happen. This is what my code looked like. When a proposal was not really sent out, or when I did not get a positive response for a promise request, I just retried. Without a retry counter, and also the coding style is not so great. What happened? I had dueling proposers. So I had a setup where I had 2 clients that issued a request at the same time to different proposers. Both wanted to have the log, Beaver and Alien. And that sounded fine to one of the instances, and then to the other, and then to the other, and then to the other, and then it went like this. So this is how it looked like. I have a small program to dump the state. I was actually running a different experiment. This is why 2 of the instances were down for some other thing that I wanted to try. And then suddenly I saw these promise and ID numbers skyrocketing, and had to reproduce it a couple of times, which is not that easy, actually, to find out where exactly the bug is. The fix, what every good SRE does, back off and jitter. Always add back off and jitter. I should have known that. Here in the example, I have some static values, but you can actually configure this. The sources for my talk. Of course, the popular paper from Lampert, Shostak, and Peace about reaching agreement in the presence of faults. I think this is not the easiest read on the world. Then, from my now colleague Mike Burrows, the Chubby log service for loosely coupled distributed systems, which I think is a great paper, and that inspired me to write my own implementation. And I can also recommend the video from Dr. Heidi Howard. It's posted in the computer file channel, which is an awesome channel full of interesting algorithms and computer videos about Paxos agreement. I don't know how many views this video has, but probably half of them is from me watching it again and again and again. She walks over the whole protocol on paper in the video, and at some point I just hit the video, paused the video, coded something, continued for a couple of seconds, coded something. So she's part of the authorship, I guess. The other video that I also can recommend is the Paxos algorithm from Luis Quesada Torres, where he goes into all the details of Paxos and also elaborates more on the different roles, more than I did. And you can also grab the code and try it for yourself and play and learn. There are Terraform modules to get you kickstarted with the infrastructure. There are Ansible playbooks to install all the software on the instances that you just kicked up with Terraform. And you can compile the SkinnyD and the SkinnyCTL tools yourself. Until the end of the conference, I will have a Quorum already running. So if you compile the SkinnyCTL tool and connect to the instances that are mentioned in the docs, so there's a ready-made config in the repository, you can use the Quorum that already is there and don't have to incur costs in firing up your own stuff. I will shut it down at the end of the conference. So this is a Quorum which already runs where you can make the Quorum agree on a value if you'd like to try it out. That's my talk. Thank you very much. Do we have time for questions? Time for questions. Questions? No questions?
So, first of all, great talk. So you mentioned the ghost quorum because of like incorrect timeouts, right? Like the timeout was like too short. How do you go about fixing that? Like, how do you, if you have like a single deployment, like, you know, you can probably just measure and like come up with like a reasonable timeout. But if your deployment changes over a period of time, like how do you keep revising those timeouts? And also if your timeout is too short, you might even never get a quorum because like, you know, your instances are too far.
Yes, I would instrument the whole code a bit, and you can count all the requests that are made to every instance in the Quorum. And if there are instances which receive significant less requests, that means that there's probably a timeout issue. But in the end, it's something that needs to be monitored in a real-life deployment of hopefully not this code. Does it answer the question?
Yeah.
Okay. Okay, cool.
Actually, sorry, I have one.
Oh,
so
sorry.
What are the next steps? What are you planning to implement now?
I'm busy working. No, I'm working on a new topic. So I consider this mostly finished. I try to maintain it a bit and maybe add some more resources for people to learn. But I don't want to add more features to keep it as easy to understand as possible.
Okay. Thank you.
But you're always free to fork it and, I don't know, add shiny gold plates to it.
I did this once and it was enough. So.
Okay, thanks.